Okay, YouTube, in this last video we're going to be looking at a couple of measurements that we look at when we talk about central angles in a circular region. So these measurements would be for the arc length around the outside of a circle of some intercepted angle that you see here, some central angle. We'll intercept an arc and we want to find the length of that, or perhaps we want to find the area of this sector, and we just refer to this as a sector of a circle, like a kind of pie slice, and sometimes we want to find the area of that. But basically, the nice thing about that is we can kind of borrow the definition of this angle in terms of radian measurement to kind of get a way of measuring this arc length. And that is to say that if we were to say that this is some angle here, theta, you notice it says central angle theta. We know that that angle theta is as big as however many times the radius fits into the arc. And so one thing I want to kind of present to you all is this, the letter S. And we're going to use S to indicate the arc length here. But we know that this angle, however many times the radius fits into that angle, that's how big that angle is in radians. And so, that being said, perhaps what we want to do is we want to be able to find out how big is this arc length. And so, to solve this for the S here, what we're going to do is we're going to multiply both sides of this by R. And what we end up with is that the arc length measurement would be equal to the radius length, however big that is, times the central angle here, theta. So that is to say that if you want to know the arc length, all we have to do is multiply the radius times the angle in radians. And so here's the important thing, at least with respect to both of these formulas here, since they're borrowing from this definition of radian measurement, the angle theta must be in radians. And so looking at this here, it says the arc length S and area A of a sector with a radius R and a central angle theta is measured in radians and are as follows. So we say that S equals R theta, which is this formula we just kind of derived here from our definition of radian measurement for an angle. And then this area formula here, which I just want to point out is very similar to the arc length formula. It's just that we are squaring our radius and we have a 1/2 that is stationed out front. But this would be the area in square units of that sector. And so here's the thing we want to make sure that we make a note of. But we'd say that theta must be in radians. And so I know that I put problems for students to work on in degrees just to see that they change it over to radians first to do these. So speaking of, let's go ahead and take a look at a situation where we might use these formulas here. So we have this situation right here. It says that a softball field forms a sector with the dimensions shown. So you see this softball field. It says find the length of the outfield fence and then the area of the field. And so of course the area is the amount of two-dimensional space the inner portion of this like sector takes up. But at least the arc length is the first measurement. The length of the fence here is the arc length. And so if we want to find this, what we're going to do is we're going to say, well, the arc length is equal to the radius times this angle here in radians. And so you'll notice that they do give us the angle. Of course, it's a 90-degree angle. But the idea here is that since it's a 90-degree angle, what we're going to need to do is we're going to need to take this times pi over 180 to convert it into radians. And so I'm going to put this over 1, and we see immediately that our degrees drop out. And I know that 90 and 180 share a common factor of 90. So 90 goes into itself once, 90 goes into 180 twice, and so multiplying straight across, of course, we get pi over 2, and pi halves, of course, is a 90-degree angle, and we should know that, but just converting it, just showing you that we get this here. So we know that the radius here, it looks like the radius of this sector is 200 feet, and we have our angle in radians is pi halves radians, and so in order to get this arc length, we're just going to say S is equal to the initial 200 feet, where we're taking that times pi halves. So we have our radius times theta, r theta. And so, you know, I guess we could throw this over 1. The 2 in the 200, 2 goes in itself once. 2 goes into 200 100 times. So we get 100 times pi, and this is in feet. So we say S is equal to 100 pi feet, or roughly 314 feet would be this length here. And so now we want the area. And so the area, it's going to be plug and chug, really. We have 1/2, and then we have r squared times theta. And so our radius again is 200 feet. I'll put this in a different color here. That's our radius. And then we had our angle is pi halves. And so throwing this in, order of operations would say that we need to do the exponent first. So we have 1/2 times now 2 times 2 is 4. And then if I took 200 times 200, I'd have 1, 2, 3, 4 total zeros. And this is times pi halves. And so let's reduce where we can. I suppose let's do this. Let's take pi halves times the half first. Because I know that pi times 1 is pi. I know 2 times 2 is 4. The reason why I want to do this is because I notice and this is in feet, and this is squared as a matter of fact, pardon me, I should be labeling this feet squared. Because we took feet times feet, we get feet squared there. But basically the 4 here. And this 4 will cross reduce. That becomes a 1. This becomes a 1 with 1, 2, 3, 4 zeros after it. But what we end up with is 1, 2, 3, 4 zeros after a 1 with a pi. And this is in square feet. And of course, it would be appropriate to get a decimal on this. So my kind of follow-up question here is, suppose the dimensions of the softball field measure 180 feet instead of 200 feet. That is to say that we moved the fence in here. Find the length of the outfield fence and then the area of the field. And I just want to kind of verify that this would be shorter, but 180, that would be 20 feet shorter than the original distance here. So it's kind of like a 10% reduction in total distance. And I'm kind of trying to represent this here. Now, we had approximately 314 feet on the fence around the first time. So this has to be less than 314. And in the area, we got, 10,000 pi square feet. So looking at this again, we'll just go about this a little bit more quickly here. We have 180 times our central angle here, which was a pi halves angle. And I'm just going to go ahead and reduce this again. We'd say 2 goes into itself once, and 2 goes into 180 90 times. So we have 90 times pi. This is 90 pi, and this is in feet. So 90 pi feet, just to show you here, if we get a calculator out here, pi is about 3.14. So if we take that times 90, we got pi. I'll use exactly pi. Here's pi times 90. We get 282-ish. So 282.74-ish. So 282.74-ish feet. And so that is, of course, reasonably smaller than this. And of course, to get the area, let's go ahead and carry this out here. But we would say that our radius is 180. This is feet, and we'd square this, and this is times pi halves. So again, we'd square the 180, and then take this times, pi fourths. I'm going to go ahead and do that. We say pi fourths. I'll go ahead and multiply these two things together first. Times 180 squared, which, I won't be lazy. We say 180 times 180. 32400, 32400. And so I would say that, I think this is a multiple of 4 here. I think 4 goes into itself once. 4 would go into this, if I just divide this by 4, divide by 4. We get 8100. So we get 8100. And so we get 8100 pi, and this is square feet, which is less than 10,000 pi. So that's sector area and arc length. Cheers.